The next couple of lessons are going to deal with something that is very, very commonly discussed on the AP chemistry exam, and something that we've brought up a few times already this year, and those are what are called intermolecular forces. So we've talked about bonding already, where bonding is the intramolecular, it's the bonds within the molecule, whereas intermolecular forces are again those forces of attraction that exist between one molecule and another. Okay? Intermolecular forces are never ever bonds. They are attractions between one distinct molecule and a separate molecule. Okay? And there's lots of different reasons that we use them. There's three main types. So in this first video, we're going to talk about the first type, and then depending on time, we'll see if we go to the second one or not. So the first type of intermolecular force that you need to be familiar with and know really, really well are what are called London dispersion forces. Okay, a lot of times you can abbreviate that by just writing LDFs, like I did right here. But anytime you're going to do that, make sure you always write London dispersion forces once, and then in parentheses, write LDFs after that. So London dispersion forces are an attraction, again, between one molecule and another molecule that are non-polar molecules. They must be non-polar. Okay? Now, and this typically it is the weakest of the three intermolecular forces, but again, there's lots of other things that will go along with that as well. But in general, it is the weakest of the three intermolecular forces. Now, when we say it occurs between two non-polar molecules, that is true. Okay, really, the true definition though of London dispersion forces, every single type of molecule, whether it's polar or non-polar, experiences London dispersion forces. Okay, but non-polar molecules only experience London dispersion forces. So whether it's polar or non-polar, it always deals, there's always London dispersion forces involved. It's when you have a non-polar molecule that the only type of intermolecular force is London dispersion forces. Now, the way that these London dispersion forces work is that basically an atom has a bunch of protons in the nucleus and it has a bunch of electrons, okay? And what happens with London dispersion forces is, for example, this drawing right here shows that I have more electrons on this side, the right side of the atom, than I do on the left side. Just by chance. That's just how I happen to draw it. So here's our nucleus, our positive nucleus here. And you can see that just by chance more electrons are on one side or the other. You kind of have a negative side over here, which results in a positive side over here. Okay? And what that is called is that's called an instantaneous dipole moment. Okay? Sometimes we often refer to it as an induced dipole. Like, we know that it's nonpolar, but still, even though it's nonpolar, if more electrons are on one side than on the other, then you do get this instantaneous or this induced dipole, that you do have a negative side and a positive side even in a molecule that is nonpolar. Okay? So again, by electrons in an atom that are briefly found on one side of the atom rather than the other. And so this instantaneous dipole moment is formed when those very small electrostatic forces, those negative charges and positive charges, by that movement of electrons within the bonds that normally, again, don't have a permanent dipole. A permanent dipole, we know that means that it's polar. Okay? And again, this is only for nonpolar molecules that we're referring to right now. So as one molecule approaches another, the electrons of one, again, are temporarily moved to one side, let's say. Okay, and again, this causes these small temporary dipoles to be set up. And again, we kind of call it an induced dipole, not a real dipole. We've kind of induced that dipole. Okay, and again, these types of attractions are called London dispersion forces, and they do exist between all atoms and molecules. So whether it's polar or non-polar, it depends. Every single type of molecule can do this. Okay, again, it's the nonpolar molecules that only experience the London dispersion forces. Now, how are we going to describe this? How are we going to use this to discuss things? Okay, first of all, there's two things you can think about with London dispersion forces. Number one, surface area. Number two is what's called polarizability. Okay, and basically polarizability means the more electrons there are in the atom, the more likely you are to have more electrons on one side than the other. Okay, so polarizability increases with an increased number of electrons. Okay, so when one atom has a larger electron cloud, which means it has more electrons, that means it's more polarizable. And the more polarizable the atom is, the more likely it is to have the more electrons on one side than the other. Okay, now we'll get to surface area here in just a minute, but let's look at an example here with the noble gases. So as you go down that last group, group 18 or group 8A, the noble gases, the atoms of these elements get bigger. So they have more electrons, okay? And with more electrons, they have larger electron clouds, okay? And what this does is this increases the London dispersion forces between them, making them more difficult to separate, which increases their boiling points. Notice that from helium to neon, to argon, to krypton, to xenon, the boiling point is actually going up. You're starting at almost starting at negative 273 Celsius. You're almost starting at absolute zero with helium. Okay, but then the boiling point, so as you go down the periodic table with those noble gases, the boiling points increase because, and this is how you would say it on a test, that xenon has a higher boiling point than the other noble gases because xenon has a larger electron cloud, which is therefore more polarizable and has therefore stronger London dispersion forces between its particles. Okay, so a lot of times, you just look at the periodic table and go, oh, well, that one has a bigger molar mass. If it has a bigger molar mass, it has a larger electron cloud. You have to be very, very careful about that. Okay, molar mass is oftentimes incorrectly to describe the London dispersion forces between molecules. Okay, you can think that way. Okay, you might end up saying, though, that krypton has a greater boiling point because krypton has a greater molar mass. Okay, that's not correct. You will not get credit for that. Although that is correct, and you can start by thinking that way, when you write your answer, you must say that the reason that krypton has the greater boiling point than neon is because krypton has a larger electron cloud that's more polarizable and has stronger or greater LDFs, resulting in the higher boiling point. Okay, so anytime you're comparing two things, even something like F2 versus Cl2, okay, and then Cl2 versus Br2, Br2 versus I2. Oh, these are all the halogens, that's right. And as you go down the periodic table, what do you find? F2 is a gas at room temperature. Okay, so at 25 degrees Celsius, gas, liquid, solid. Why does that happen? Why, as you go down that periodic table, you go from gases to bromine being a liquid to iodine being a solid? Well, F2, Cl2, Br2, and I2, completely non-polar. Okay? And so the only type of intermolecular forces are London dispersion forces. So as you go down from fluorine to chlorine, chlorine to bromine, bromine to iodine, the size of the electron cloud is getting larger and larger and larger. And as it gets larger, what happens is that the strength of the London dispersion forces increases. So of those four, I2 has the strongest London dispersion forces, where fluorine would have the weakest London dispersion forces. And how would you describe that? I2 has the strongest London dispersion forces because it has a larger electron cloud than the other three. Therefore, it's more polarizable, and the strength of the LDFs is greater in I2. Okay? So anytime you have an atom by itself, okay, helium atoms, neon atoms, those are, again, they're not bonded with anything. Those are nonpolar. Okay, anytime you have molecules that are nonpolar, you're always going to talk about London dispersion forces. Okay? So, now let's talk about surface area. What happens when those electron clouds are similar in size? And how do you know if they're similar in size? Because they have similar molar masses. Okay? If you look at two different compounds, you're like, well, wait a minute. Their molar masses are about the same. Why does one have a greater boiling point than the other? Okay, then now we go to the second reason for London dispersion forces, and that is surface area. Okay, a molecule that's more spread out will have a larger surface area than a molecule that's all clumped together and therefore has a higher boiling point. So larger surface area, the higher the boiling point. Okay, for example, these two compounds right here. And again, I'm not going to draw the whole thing out, but basically this first one here looks like this. It's got a carbon, 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 and then another carbon with a bunch of hydrogen. So that one's really, really clumped together. Okay, whereas this one, 1, 2, 3, 4, 5. Yeah, and so there's our 5 carbons again, all clumped together. Whereas C5H12 is carbon, 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 carbon. Okay, like that. Okay. So the first molecule you can see has a boiling point of 10 degrees Celsius, whereas the second molecule has a boiling point of 36 degrees Celsius. Okay, why the difference? When their molar masses are virtually the same, if they're not exactly the same, their molar masses are exactly the same, is the fact that C5H12 is more spread out and has a larger surface area, so therefore it has more points on its molecule where it can form London dispersion forces of attraction with other C5H12 molecules. And the more area that it has where it can form those instantaneous dipoles with other molecules, the stronger the London dispersion forces will be. Okay, so London dispersion forces, two things. Number one, typically it's this one, it's the size of the electron cloud. And again, use the molar mass on the periodic table to use that, to determine the larger the molar mass, the larger the electron cloud is going to be. If the molar masses are the same and therefore their electron clouds are similar in size, then you go to surface area. Okay? So of the three, London dispersion forces is typically the weakest, but not always. We're going to see in our next video when we talk about the next one. You can see it right down here. Okay, when we talk about that one, we will kind of talk about some times when is London dispersion forces stronger than this next one, and when is it not?